Good morning, everybody. My name is Hatton. I'm a PhD candidate in the Department of Chemical Engineering at MIT. And today I'd like to talk to you a bit about our research innovation in the field of redox active materials for targeted electrochemical water remediation. So firstly, chemical separations are ubiquitous in the manufacture of chemical as well as pharmaceutical products. However, the drawback is that chemical separations are often very energy intensive. And so this leads to very severe negative repercussions in terms of economics as well in terms of environmental considerations. Specifically, the area of removing trace contaminants from water has been highlighted as a crucial separation area for technology improvement. More recently, the EPA conducted a study on a domestic body of water, and they found the presence of a large amount and large variety of chemical compounds. These compounds fell into two general categories. One would be compounds resulting from agricultural use, such as herbicides and pesticides, with the other being general chemical, pharmaceutical waste products, as well as household personal care products. And so the issue here is that all of these chemical compounds are charged species, they're micropollutants, present in usually very dilute concentrations, and because there are so many of them, they act as competing species. And so the challenge is that it is very difficult to remove these species effectively and also quite expensive using conventional methods. So currently, techniques such as reverse osmosis, fixed bed adsorption, capacitive deionization are all technologies that we can use to remove charged species from the water. And so in the case of capacitive deionization, what happens is that a porous electrode is charged with a potential or a current, and then ions are then adsorbed to the surface. However, some of the drawbacks with this method are that the energy costs required are quite intensive, and in addition, there's a lack of selectivity in terms of the ions that can be removed from the water. Similarly, reverse osmosis is also problematic in the sense that there's low efficiency in dilute ion concentrations, and in the case of fixed bed adsorption, it also requires the need for expensive chemical regenerants. So how we propose to combat and tackle this problem is to use our redox active technology to selectively separate ions from competing species in water. And so the separation factor for these targeted ions is very high over the whatever competing species we have in the solution. And compared to the base case, which is the capacitive deionization technology, which has a selectivity of 0, the separation factor there is essentially none. And so this is based off of technology that we developed within our group, the Hatton Research Group in Chemical Engineering, where we developed nanostructured redox active electrodes that have high capacitance and high charge. So moving forward, we definitely like to extend our technology and scale it up to an electroseparation device where we can flow in contaminated water to a multi-stack continuous flow system and retrieve clean water on the outlet. To establish some market context, the industrial wastewater treatment market is definitely a big and very worldwide market, with two key players being the US and China. A key subset of this wastewater treatment market would be the chemical and pharmaceutical wastewater treatment markets. We've already established contacts with many stakeholders in this industry, both domestically as well as internationally, who have interest in developing our technology further for their own applications. To further validate our redox active technology, we decided to select a couple of target molecules based off of the two categories that we observed from the EPA study in terms of the chemical compounds that they discovered in their body of water. And so we selected a herbicide, a pesticide, a chemical detergent, as well as a pharmaceutical that also acts as an endocrine disruptor. And so using our redox technology, we conducted several experiments, and these are real results, and we see that using the redox active technology, selectively we can obtain a much higher recovery fraction, as shown in red, compared to the base case, which is just capacitive deionization, which is seen in blue in the chart. So over here, we see that the selectivity is enhanced multifold. In addition, our technology can attack a wide range of contaminants. So we've already seen the anode technology, which attacks anions, negatively charged species such as pesticides and drugs, but we can also apply this to chemical and food products as well. On the other side, we also have cathode technology, which can attack positively charged cations. And so this can include things like valuable or toxic heavy metal ions, as well as more complex organic charged species. Our electrodes are very robust. They can withstand more than 5,000 cycles without loss in absorption performance. And also, in comparison with a more conventional pressure-based technology such as reverse osmosis that we mentioned before, there are also energy and cost savings involved because of lower operation and energy usage. Furthermore, our electrodes are quite energy efficient and also are relatively inexpensive to make, which further add to these savings. So to summarize very briefly, in our lab, we've already established a fundamental science-level proof of concept of the separation mechanism. We've upgraded that to an analytical scale batch and conducted experiments there. We've made a preliminary continuous scale, bench scale prototype, and we're now in the process, with the help of JWAF Solutions and another grant, in developing a continuous regime process scale demo. Moving forward, we'd like to scale this up even further to a multi-stack system for continuous flow applications. So this is our core team. The work is led by a postdoc in our group, Xiao, and I'm a PhD student in the research group as well. And our research advisor is Professor Hatton, who's also the director of the Chemical Engineering Practice School at MIT. So with that, I'd like to thank you very much for your time, and I look very forward to discussing with you all afterwards. Thank you.